I'm going to be presenting two research studies that were carried out by two graduate students in the Department of Civil and Environmental Engineering. One towards her master's degree, her name is Harajli, and another one towards his PhD, his name is Suri. And both studies are concerned with earthquakes and seismic hazard and seismic design. You know, Carla Hayer joined me as Carla Hayer, but she left as Carla Hayer Shadi with two kids or two babies. So this is how things go in research. But I'm very proud of what she has done. I'm also very proud of the achievement of Amr Suri. How do you move this? I'm going to talk about the seismic hazard evaluation in Lebanon, starting with 1994. We did a study at AUB at the beginning of the reconstruction program in Lebanon. So I'm going to talk about this stage of the evaluation of seismic hazard, and then I'm going to move to where the seismic hazard stands today in light of new developments or new discoveries regarding the tectonic settings of Lebanon. Let me start from a very basic perspective. Why do we evaluate the seismic hazard? Earthquake forces produce ground acceleration. And according to Newton's first law, when there is acceleration, there is what? There is inertia force. Therefore, the ground acceleration, which is the ground shaking, which goes in the horizontal direction, applies inertia forces, lateral inertia forces on the structures, whether these structures are bridges or buildings or any kind of structure that has mass. So the force of the earthquake on these buildings, in a very basic manner, is the mass of the structure m times the ground acceleration. So we need to know what is the most probable ground acceleration that the structure will be subjected to during its lifetime. So what is seismic hazard? Seismic hazard, why it's important to quantify? Why it's important to quantify? Because the engineering community need this parameter to design their structures. Before 1994, this parameter did not exist at all. Even the people, the engineering community did not know that Lebanon is vulnerable even to earthquakes. So we need to quantify this parameter. We need to know it because the engineers need to have it for design of their structure. And this is, so we need to evaluate it based on a design life of the structure of 50 years. Now, if we evaluate it too high, then there are economical implications. I mean, we start losing money as a company. We are designing and constructing buildings for something that maybe will not take place during the lifetime of the structure. If we evaluate it too low, there are safety implications. We don't want our structures to collapse in the event of an earthquake. So this is the whole story. Now, please move. So what are the parameters that influence earthquake hazard at a specific site? We have the presence of active faults, seismic sources. We have to know at that time, in 1994, what are the active faults in Lebanon. And we were able to do that. And then we have to determine what is the maximum magnitude earthquake that can be triggered by any major fault in Lebanon. Also, we need to know the distance of the site from the earthquake sources. We need to know this because there are attenuation equations that tell us if an earthquake takes place in Cyprus, it is not the same intensity in Lebanon as it is in Cyprus, because earthquakes die with distances. That last earthquake that took place between Cyprus and the coast of Lebanon was measured 5.5 in the epicenter, but it reached Lebanon very, very mild. I mean, we barely can feel it, but some people felt it, some people not. We need to know the dynamic characteristics of the structure. This is something I'm not going to dwell on. We need to know the soil type and the classification, whether rock or soft soil, to be able to quantify the hazard. We need to know the recurrence of the earthquakes. Large magnitude earthquakes occur less frequently than medium or low magnitude earthquakes. For example, 7.5 in Lebanon may occur every 300 to 350 years, while 3 or 2 are occurring every second we are talking here, and they are measured by Hannes Observatory. So all of these relations are important if I want, or all of this information becomes important if I want to evaluate the seismic hazard of Lebanon. So in 1994, we needed to collect all this information. First of all, where does Lebanon stand? I mean, is Lebanon, we are here blessed apparently by a major fault, blessed in the sense, in addition to the political, social, economical blessing of Lebanon. We have a major fault that passes in the middle of the Lebanese territories. You know, it is part of what we call a major Dead Sea, Jordan Valley Dead Sea fault system, which extends from the Gulf of Aqaba. It passes between Israel/Palestine and Jordan in the middle, and then it enters Lebanon, and then it continues to Gulf Fault, to Syria, where it's known as Gulf Fault. In Lebanon, it is known as the Amuni Fault, and then it joins the Anatolian Mountain in southern Turkey. The fault is 1,000 kilometers long. And we know that this is moving upward relative to this plate. It's a plate tectonic here, like this is a plate boundary, about 5 millimeters per year. You know, the geologists talk about this. There are many theories about its formation, etc. We're not going to talk in detail. Please go ahead. Now, so as you can see, the fault that I'm talking about is a plate boundary between the Arabian plate and the African plate. And whenever there is a plate boundary, it means there are earthquakes. When it enters Lebanon, this major fault, when it enters Lebanon from the Jebel Jalil, what we call the Galili Heights in southern Lebanon, it forks out into several faults. There is Rum fault, there is the main Yamuni fault, there is Rashaya, Hasbaya, Sargaya, etc. And all of these trigger earthquakes. So this is the this is a map showing the epicenter of earthquakes that occur in this part of the world. This is the Alpine belt. So our region is earthquake vulnerable, and this is what we. Well, let us give you some examples of past earthquakes, just to show you the devastating nature of an earthquake, and which I'm sure you all know. Go ahead, Shway. This is one of the failures due to an earthquake. I don't know which country it is. This is Kobe in 1995. This is a bridge structure which collapsed totally because of the earthquake. It measured at that time 7.2. This is again the bridge of the same bridge. This is the photo of the same bridge, or a slide of the same bridge. You can see how this is a landslide caused by the earthquake. This is a spans of the bridge that collapsed totally. I mean, this is what the earthquake will do, and this is what we do if it strikes Lebanon. This is the Niagara earthquake in 1964. We see how the bridge panels or the deck slabs collapsed into the river. This is maybe recently, it looks like it's either in Haiti or in somewhere, I don't remember. You can see this bridge collapsed, and you can see the cars. Please move on. This is Kobe earthquake. This is an entire bridge pier that failed because of bad design, apparently, because of bad detailing of reinforcement. This is a riverbed uplift of about 4 meters, you know, things. This is Bam earthquake. This is a castle in Iran. This is before the earthquake, and this is after the earthquake. It disappeared completely. But again, this is a stone structure, and we don't expect our buildings to suffer the same destiny. This is a church or a mosque, or I don't know where. It's, you can see it's partial collapse. This is a building that's stiff at the top. I'm giving you an example of earthquakes to show you how stiff at the top. So the entire building moves as one body, putting too much stress demand on the columns at the basement, at the ground floor, causing what we call soft ground story failure. And this we should avoid. This shows how the tilt of this person standing here. Please go ahead. This is in Turkey, 1999. Again, you can see the entire building tilting. This is Mexico City in 1985. The entire building pulled out of its foundation. And Turkey, we can tolerate everything as engineers, but for the building to collapse in this manner. And this is not allowed. This is Izmit in Turkey in 1999. You can see here, I'm giving you examples of the major earthquakes. 1970, 7.8, 67,000 people died in Peru. In Bangladesh, 300,000 to 500,000 people in 1970. We don't know the magnitude of that earthquake. And the list goes forever. India, 2001, 7.7, 20,000. Haiti, 2010, 250,000 people died. This is, of course, in addition to the property damage, which is estimated in billions of dollars. So at that time, we asked ourselves, would our buildings in Lebanon hold in 1994? We did survey of our buildings, especially that is why they are vulnerable in Lebanon, our buildings. There are minimum or no shear walls. Shear walls are the most important structural elements that can resist earthquake. Nowadays, we are advising the Lebanese government, not the Lebanese government, the engineering community to try to depend heavily on shear walls. Based on our experience in this area. Our columns are very slender, they are not good because the main elements that will resist the earthquakes are the vertical elements, shear walls, columns. So unless these elements are properly designed, the buildings may suffer collapse and damage. Partition walls are heavy and may be concentrated at the above the ground level, what we call soft ground story, and we show them examples of this kind of situation. Buildings are highly irregular in shape, and irregularity attracts earthquakes, stresses in a way that we can't really predict. Buildings are adjacent in heavily populated areas, and building adjacency means what? That buildings can hit each other during the earthquake because of their vibration, causing what we call pounding damage. Pounding damage contributed to 15% of the failure in the Mexico City earthquake in 1985. Loose soil deposits and potential for liquefaction. Fortunately, Lebanon is, as Dean Sweden mentioned in the last lecture by Freddie, is that it's 80% of Lebanon soil is rock, and rock is good for earthquakes. We don't expect too much amplification of the earthquakes, and it is better than loose soil deposits. So it was time in 1992 to start develop an earthquake. In 1992, we thought about it at the UB. There was a team that was formed, myself, Dr. Sadiq, Dr. Munir Mansour, with the help of graduate students. We attempted to develop a seismic code. So we have, especially with the start of the reconstruction program after the Civil War, we said that if there are structures, new structures to be built, they better be designed for earthquake. So we first in 1994 we conducted seismic hazard study, probabilistic in its nature. It has to be probabilistic. We collected an earthquake catalog. We identified the seismic sources. We established attenuation relationships, the most applicable for the region in which we are studying, which is Lebanon. And again, this is what I've shown before. We have shown this before. We collected instrumental data from 1903 until 1991. We got all this data which we need to understand the recurrence of earthquakes. These two earthquakes here occurred in 1956. In 1956, which are the double shock earthquake that took place in Champaign at the tip of Rumford, and they measured about 5.9 to 6 on Richter scale. They are the only earthquakes that were felt during our lifetime, I suppose. But of course, there are earthquakes in history. There are earthquakes in history that if we go back to 1,000 years ago, 1,100 to 1989, we see there are many major earthquakes that struck Lebanon. For example, in Hama, in Idlib, in Baalbek, in Hatab, in Orontes, this is in Turkey, in South Biqa, in Ledri, in Syria, in Champaign in Turkey, also in Turkey. So all of these, based on historical accounts, they all measure above 7 or 6 above 6.5, let me say. The last major one that struck Lebanon in this century is 1759. There were two earthquakes, one in South Lebanon and one in the Bekaa Plain. And if we say the recurrence period of major earthquakes is about, 250 to 300 years, we are in the recurrence period for a major earthquake, but this could be plus or minus 100 years. You cannot just say tomorrow it's going to happen. Please go ahead. We took the sources in neighboring countries, the seismic sources. That earthquake that took place a few days ago belongs to the Cyprus region. It doesn't belong to our fault system at all because it's 150 kilometers away from the coast. We took Syria region, that fault, we took the Dead Sea fault, and we came up with the seismic hazard of Lebanon, which is in the next slide, please. Attenuation equation we used, never mind this. And at that time, we came up with simple seismic hazard model. We zoned Lebanon into 3 zones, 0.15, which is low moderate, 0.2, moderate to high, and 0.255, but 0.25 only in this region here. But based on discussion with the Lebanese government and people in charge, we decided to zone Lebanon as one seismic zone, which is zone 2, which corresponds to zone 2B of the Uniform Building Code of the United States. And the entire country followed this seismic zone accordingly, and every building and the structure that was designed and constructed in Lebanon followed this seismic zone parameter. So if an earthquake happened, they will take us to jail now. Go ahead. So this is what we recommended at that time. Let's go. Now, this was adopted on May 26 by the Council of Ministers, Decree number 103, that we should adopt this zone and seismic design of our structures in Lebanon. Also propose some design and construction guidelines, but these are very primitive in nature, just for the engineers that don't know earthquake design to try to understand how to detail the reinforcement, etc. Of course, any engineer can use his own. So this is the most important parameter to be moved. Now today what happened? Today we discovered a new fault. And this is the work of Ms. Carla Hadi. There was a French expedition that came to this part of the world about 4 or 5 years ago, or 6 years ago, I don't recall. And they found out there is a major fault across the coast of Lebanon, about 15 to 20 kilometers away. So we proposed to the National Council for Scientific Research to conduct a study to try to update the seismic hazard. What is this fault? This fault is here. It's again 15 to 25 or 30 kilometers away from the coastline. This is what we call a thrust fault. Yani this is moving in this direction, this is moving in this direction. So when there is earthquake, there is a thrust, it can trigger tsunamis. And tsunamis, you know, I mean, hopefully it doesn't happen. And historically, Lebanon was struck by tsunamis in the past. This is what the geologists tell us. So this fault has important implications on the seismic hazard on the coastline, because this is where the population is concentrated, and this is where the capital investments are. So if we take a section of this fault, I want to show you this fault. This is not vertical at all. If we take a section, please. If we take a section of this fault, we see that this is the fault. It's oblique. In other words, it extends, it has a surface impression here on the sea, but then it runs what? It runs at an oblique angle, joining the Amuni fault line, which is vertical. Therefore, all this region is falling what? All this part of Lebanon is lying on a major tectonic fault, and this is dangerous. This has a great implication on the seismic hazard. So we took that into account. We collected, again, the instrumental, we updated our catalog, you know, with the help of Hannes Observatory. Please go ahead. We took all kinds of earthquakes. This took about 3 years of study, I mean, of research, and then we took the major earthquakes, again, like we did in the past. We updated also our catalog. We found there are earthquakes that were not accounted for. And we used the most recent attenuation equations, which are very important, by Carr and Bomer, 2008, 2010. These are, we took all of these and we tried them, and we came up with a new map in accordance with the Uniform Building Code. You see, this is the isosysmal maps. They are very important. Again, this is for 50-year lifetime. For Beirut, you know, especially for the Solidaire area, we did a study for the Solidaire area to try to zone Solidaire, because they're very expensive buildings over there. They asked us to do some study, and we did it. Okay, now if I compare with the past, you see there is a major difference. So we are proud of what we achieved. Please, if we are, Al-Nashai and Al-Khouri. Al-Nashai is a professor at the, he did some study with, Khouri, from Rafiq Khouri and partners. He came to Lebanon and he did a study. He is a professor, the head of the Earthquake Engineering Research Center at the University of Illinois, Urbana, Champaign. Again, he got results similar to what we got in 1994 because he didn't know of the fault that's occurring over here. So we went to the engineering community very recently and we told them, you have to use Z equals 0.25, which is about 22% increase of 20, I mean, there is sizable increase in the seismic hazard. We cannot go to 0.3 because the engineering community will not design for 0.3. It becomes very stringent, very economically expensive. We have to go gradually. So I'm going from point to the next steps in 5 or 10 years, and this is a political decision, we may go to 0.3. So the engineering community took this figure, and Lebanon adopted it, and now it is becoming the norm in Lebanon. Lebanon now is designing according to 0.25. Experimental study, I'm going to go very quickly in this. The PhD study at AUB, we evaluated the earthquake resistance of our current buildings in Lebanon. And this is a PhD study by Dr. Amr Souri. We evaluated what would happen to our buildings, our current buildings if they are struck by an earthquake, and how can we improve these buildings in when we want to make them seismically resistant. So this is a building. These are the buildings that we took. Example of the buildings. We isolated this frame over here. When there is an earthquake, the location and the structure where will suffer most due to earthquake is the beam column joints. There are beams and there are columns, so it is this region over here. So we can isolate all of this, and we also can isolate this and study them in the lab. And we can take the entire building, we can take only a small frame of the building to simulate the building, put it in the lab, and this is full scale, and study its response under earthquake load. And we have the facilities in the materials and structural lab to do that. This we did. So this is a reaction wall where can apply the earthquake load. I can simulate the earthquake. It is not really an earthquake, it's a quasi-static. And we apply it gradually to take measurements. And there's a stronger floor. So we put the specimen, we subject it to load, to cyclic load, simulating earthquake, and we study how would this specimen perform, which represent our current structural system. Also, this is for the exterior joint. This is that. So this is the specimen. You see, it's a full scale. It's about 3 meter high, 3 meter wide. And we found out that when we subject it to earthquake, our existing structure, look what happened. There are great damage that will take place in the joints. The joints are not at the current design and construction practice. The joints are extremely weak, so they cannot. Again, not every one of you will understand what I'm talking about, but this is to show you that we have good quality research going on in our lab. So this is something that full-scale testing, and we also are happy to have achieved the results, this kind of results. So they are not good, please, but when we repair them for earthquake, when we strengthen them for earthquake, we provided some reinforcement at a very low cost, with a very low labor, with a very little labor, and without changing our structural system, it is very easy to make our buildings much stronger against earthquake. You see the cracks, there are cracks. We cannot avoid or escape cracking in the structure. But again, they performed excellently with a very little effort and money and cost. So you can see these are the earthquake resistant joints. These are the current. You can see how the load capacity decreases very quickly. While if I provide reinforcement, you see this performance is just as extremely good because it's stable. There is no loss in load capacity with increasing drift of the building. This is the column, the load that I can apply, the earthquake load. It's a stable behavior. While for the current structure, this is the envelope line. I'm not showing all the slides over here, which shows that it will collapse immediately. So if we look at the load capacity of these we can see that the as-built joints, this is how much they can take load, while the earthquake-resistant joints can take significantly higher load, and they are much more stable, and they can survive earthquakes. As-built joint major findings are expected to experience large damage beyond repair. They cannot be considered as part of the earthquake load resisting system, and therefore we We should do something about them. The earthquake-resistant joints, with a slight improvement of the reinforcement detailing of the as-built joints, the joints performed adequately and considerably better than the as-built joints. This improved performance manifested by considerably larger load deformation and energy dissipation capacities and much lower and repairable concrete damage. We even repaired these after they were damaged. We repaired them and we tested them again, and they performed beautifully. Thank you. Hopefully you don't feel an earthquake